Hi, I'm Andrew Wells, and I'm going to talk to you today about finite-horizon synthesis for probabilistic manipulation domains. Let's consider a classical example of a robot task planning. Here, the robot is told to do something such as cleaning a table. It breaks down this task into a sequence of actions it can take to accomplish the task. For example, pick up and put down actions. And then for each action, it computes a motion plan, which will take it geometrically from the start state of that action to the goal state of that action. In these examples, the robot is looking at sort of a linear path from a start state to a goal state, where each state has a single successor state. In contrast, for this talk, we're going to mostly consider policies. So sort of abstractly, a path is what we have on the left, or a plan is equivalent to a path. So the robot is in one state and it's told to do a goal, for example, retrieve a banana. And it thinks of, in this example, one banana it wants to retrieve and the actions it will take to go from its initial state to the goal state, assuming everything succeeds. On the right, we have what is a policy, which is a mapping from a state to action. So basically, this is useful if something might go wrong. If something goes wrong, the robot could find itself in an unexpected state, and it wants to know what it should do from this unexpected state. So if we have an action to perform in every state, then we're sort of covered. No matter what goes wrong, we know what we should try to do. So specifically, in this talk, we're going to talk about synthesis. We're given some tasks to accomplish and some abstract model of robot actions and the possible outcomes of those actions. And our output is going to be a list of the actions we would take in every state or a policy, and this will be optimal with respect to some criteria. For example, the probability of task completion. So there are several different ways we could go about solving this sort of problem. The first is replanning. This is probably the most common. Here we sort of start at our initial state and just compute this linear plan from the initial state to the goal state. And then from that, we can look at what happens when we're actually executing that on the robot. And we see that maybe we expected to end up in state S, and instead we end up in state S prime. So what we do then is we say, okay, something went wrong. Now I'm going to compute a new plan from S prime to the goal. So this is good in terms of scalability because we're only computing one plan at a time. It's much cheaper to compute plans than policies, but it has several downsides. The first is runtime latency. So if we have to recompute these plans on the fly, we have to sort of pause and think about what we're doing. And then guarantees of task completion or of task sort of cost estimates. If we aren't considering what might go wrong in the future, we could end up making something that's suboptimal. And in the worst case, we could do something that has sort of infinite cost to reverse. So if you consider something like cracking an egg, the robot has no way to uncrack an egg. And in some domains, you could maybe have a task which would be possible to guarantee completion of, but if you use this replanning approach, you're not complete. There might be scenarios where it's not going to complete the task, even though it was possible to complete the task. One way to sort of address those limitations is contingency planning. So here, basically, we think about some of the things that might go wrong and how we would address them. We do that by having sort of a backup or a contingency plan. For example, an autonomous car might have the contingency plan of slamming on the brakes and continuing under the current heading. So this gives us sort of worse scalability, of course, because we have to think about sort of what might go wrong and how we'd respond to it. But if we sort of do it right, then we'll have very low runtime latency because we thought about these things beforehand, and we'll be able to guarantee task completion. And reactive synthesis is sort of along the same lines, but we'll use techniques from formal methods to sort of think about the things that could go wrong systematically and to improve scalability. So there are two elements of reactive synthesis. The first is this domain abstraction, and the second is this LTLF, or some logical task specification. And our goal is to find a strategy that guarantees task completion. So let's start by talking about the specification. In linear temporal logic, we have this timeline of instances in time. So these are discrete instances, but they're not necessarily evenly spaced. And at each instance, we have some Boolean variables. So here, A and B, that can either be true or false. If they're true, we write them in curly braces above the timeline. If they're false, we omit them. So at T0, A and B are both true. At T1, A is true and B is false, and so on. Then we're given some logical formula. For example, A implies next, not B. We want to ask whether a trace above is a model of this logical formula. Here we see that it is, so we can sort of just work through that. At the first time step, A is true, so we have to look at the right-hand side of that implication. Next, not B, so we look at time 1. We see that B is false at time 1. The second element was the domain abstraction. So here basically we have states, and we look at how the states can evolve. And this can be the result of either agent, the robot agent, or the human agent taking actions. So you can think of these agents as players in a two-player game. In order to solve reactive synthesis problems, we have to place some restrictions on the human. So the first two of these restrictions are pretty straightforward. So the human can't move something so far away the robot cannot reach it. And the human cannot hold on to an object indefinitely because we never have the robot try to grab something from the human. And then the last one is a little unintuitive, but basically the idea here is that if we allowed the human to take as many actions as it wanted, it could always undo robot's actions, and the robot would never be able to make progress. So we give some finite parameter k, limiting the number of human actions. And the robot is sort of modeled in the standard pick-and-place domain. This is how we've done things in previous work. But that k is very unintuitive. So you could ask, are there ways we could eliminate this? And one way to eliminate this is to move to a probabilistic model of the human. So here we have one agent, the robot, making actions. And then we have probability distributions that capture different aspects. We can capture sort of the probability that the human's done acting, just the general probability of human actions, probability of other disturbances in the environment, or probability of, say, the robot failing to accomplish something it tried to accomplish due to mechanical failures or something like that. So the key intuition behind why we want to look at probabilistic versus reactive synthesis is that in reactive synthesis, we're very pessimistic. We assume the human is adversarial. So in this, we sort of stylize this on the left. The robot tries to build this arch far away from the human because it knows this discourages the human from interacting with the arch because the human has to reach further. And this makes sense if the human is assumed to be adversarial, or if we have a probability distribution that sort of effectively says the human is more likely to be adversarial than beneficial. If, however, we have some description of the human which sort of informs us that the human is likely to be beneficial, then the robot could instead do what it does on the right here, where it tries to build the arch near the human, and this leads to more effective collaboration. So in order to formally talk about how we model this problem, we need to introduce our state space. So basically, we consider several regions of interest. So here, sort of locations 2, 3, and 4 on the left are locations of interest for accomplishing a task. Location 0 is inside the robot gripper, and then location 1 is what we call the else region. This is basically all of the regions not specified explicitly as some other important location of interest. Now, to represent a state on the right, we're going to sort of draw the colors of different objects at these different locations. And here we have 3 objects, red, yellow, and blue. Blue is not drawn, and everything that's not drawn is going to be assumed to be in the else region. This will be a nice shorthand to show diagrams like this. So here we start with blue in the else region and red and yellow at 2 and 3. And now the robot can take an action, say at the top center, to grasp the blue object, and then take another action going to the top right to place the blue object on top of the red and yellow objects. And in this state, we draw 2 circles to show that it's an accepting state, or that it satisfies our specification. Now, turning this into a probabilistic model, we could capture something like a probability of robot failure. So here we're going to label edges with probabilities, and we're also going to have labels for arcs coming out of each state for the name of the action that is performed. So for example, from that top center state, if we attempt to stack the blue object on top of the red and yellow objects, there's maybe a 90% chance of success, in which case we've accomplished our task, and a 10% chance of failure, in which case we stay in the current state. We also want to model humans with some distribution. So this is taken as input by our algorithm, but for example, we could have something like this. Maybe the human has a 40% chance of doing nothing in the states shown on the left, maybe 15% chances of moving individual objects shown in the bottom and rightmost states, and then smaller, maybe 3% chance for these ones of taking sort of compound actions where the human moves more than one object in quick succession. So combining those robot and human models has sort of 2 main challenges. The first is in deciding whose turn it is, and the second is in deciding how to resolve conflicts. So to decide whose turn it is, we sort of note that our state space has this Boolean property of an object being in a location or not being in a location. So this sort of implies that an action such as opening or closing the gripper for the robot is going to be atomic. And then all other actions we're going to sort of make non-atomic to give the human as much flexibility as possible. In order to resolve conflicts, we sort of note that the robot only knows that a conflict has occurred if it sees an unexpected change in the state space. So the robot, whenever it sees this change, should intuitively take advantage of this new information it's received. So we have the robot always defer to the human. So again, giving the human as much flexibility as possible by having the robot recompute what it wants to do whenever it observes a new unexpected state. A natural question here is what happens if the human model is unrealistic? So maybe we move to a state that was assumed to have probability 0. In the worst case, we won't have an action to take at some unreasonable state, so our method could fail. But in more typical cases, the probabilities will be sort of nearly aligned with what we're given as our input, and in those cases, we'll have reasonable responses, although we won't be able to make guarantees of optimality. So in combining the human and robot MDPs, we could end up with an MDP sort of like this. So here the robot is attempting to grasp and place the blue object on top of the arch. There's maybe a 36% chance of success, and then there's maybe a 4% chance that we stay in our original state, 15% chances that the human makes some action which sort of disturbs the robot, makes it unable to accomplish this. This could also result in the state at the top right, where the states of the red and yellow objects aren't observed to be changed, but we saw that the humans maybe moved and then replaced it, or somehow interfered with the placement location of the blue object. So the robot only half completed its task. In order to improve scalability, we're going to rely on binary decision diagrams. The key insight here is that our transition system and automata are both given with respect to Boolean variables, so our computations are concerned with Boolean functions and sets. And BDDs are a popular way to sort of compactly represent Boolean functions and sets, but they're sensitive to variable ordering. So in order to examine variable ordering, we're going to look at a few different encodings we could use. The first is the integer encoding. So basically we map each state arbitrarily to an integer. This is the default. It's sort of the best you can do if you don't have any extra insight about your state space. The next is the object to location map. So here for each object, we tell you which location it occupies. And the third is the location to object map. So for each location, we tell you how many objects are at that location. Now we look at a few different experimental scenarios, and then we examine the runtime and memory usage of these different encodings. So as you can see, looking sort of the bolded numbers are the best in each category. The integer encoding has the best memory usage for very simple problems, but quickly times out as we get up to the example C, which is 5 blocks. The size encoding is sort of the second best memory usage in general, followed by the location, or sorry, the object encoding has the second best, followed by the location encoding. But typically the memory usage is sort of comparable between those two, whereas the runtime for the location encoding is typically much faster than the runtime for the object encoding. So typically the location encoding is sort of our best choice because we frequently have maybe like 32 gigabytes of RAM in this example. And we don't care whether we use 25 gigabytes or 29 gigabytes of RAM, but we would like to solve it twice as fast. In conclusion, we introduced a framework for probabilistic synthesis for robot manipulation. We examined some different encodings for symbolic synthesis, and we have made our tools available on GitHub and also provided a Docker image if anyone wants to test out our tools. Thank you for listening.